Hello. In this video, we are going to talk about the basic operation of the MOSFET transistor, first in a qualitative way. So I have drawn my MOSFET transistor, a two-dimensional cross-sectional view of it. And we have talked about how the principle of operation of the transistor was that an input voltage applied at the gate. So I'm going to write down here principle of operation. Was that the input voltage applied at the gate will control the flow of current between drain and source. So gate voltage, which is the input, controls drain to source current, which is the output. Now, typically, when we refer to a voltage, we refer to a voltage with respect to some reference point. And so when I talk about the input being the gate voltage, more correctly is the delta between the gate and source voltage. So we will label VGS. But let's take a look at, so I'm going to write my input signal will be VGS. And my output signal, you can refer to it as IDS or sometimes for short, as opposed to labeling current from drain to source. Sometimes it's just simply referred to as ID, the current flowing through the drain, with the understanding that it is equal to the current flowing through the source. Let's go ahead and assume first that I don't apply any voltage to my transistor. So all my terminals are sitting at a voltage of 0. They're all tied to ground, let's say. And under these conditions, the transistor is off, and so there is no conduction of current. So for Vg equals 0, or I should say VGS, I'm going to start referring to it as VGS. Equals 0. There is no current flow, meaning the current from drain to source is equal to 0, and therefore we say the transistor is off. It's not conducting any current. In order to turn on the transistor, we need to start increasing our gate voltage, our input voltage. And so let's imagine that I start increasing my gate voltage. And in order to do that, I'm going to connect a voltage source here, which I'm going to call VGS. My source is just sitting at the ground for now. Try to do a little bit of a better job there. All right. And now, as VGS increases, we can see there is going to be no current flowing into the gate of the transistor because we have that silicon layer, that layer of insulating material. However, as I apply a positive voltage, a more positive voltage on the gate terminal of my transistor, what I am creating is an electric field. An electric field is pointing in the direction of flow of electrical current, or the direction of the force that a positive charge will experience, right? And so if I have a more positive voltage over here, my electric field is being created pointing from gate to the channel underneath to the substrate. That's my electric field. As I keep increasing my VGS, my electric field grows stronger and stronger. And what's going to happen is that it's going to start attracting negative charges to this region. And those negative charges are going to start filling the holes, the excess holes that I have in my P-type substrate, right underneath the gate region. There are going to be negative charges coming to fill those holes, but in essence what I'm going to be left with is a region right underneath the gate that is overall negative. The net charge is negative because I have attracted electrons from all over the substrate towards the gate, which have filled the holes, the available holes there, but have given me right underneath the gate a net negative charge. And that creates a continuity of n-type material between source and drain, so that if I apply an electric field between source and drain, now the current is able to flow from drain to source. Unlike the previous case, before I applied any voltage to my gate, what I had between source and drain was two back-to-back diodes, right? Before I applied any voltage, all I had was something that looked like this, two back-to-back diodes. And therefore, it didn't matter what voltages I applied between source and drain, current wouldn't be able to flow. If I increase my drain voltage with respect to the source, still one of the diodes will be non-conductive. If I increase the other voltage, the source voltage with respect to the drain, the diode that is next to the source will become non-conductive. So I could never have current flow, but now, since I have a continuity of n-type material, I can have some current flow if I apply the right electric field or the right voltage difference between drain and source. And so we say I have induced a channel. So by virtue of applying a voltage at the gate, I have created an electric field which has induced an n-type channel underneath the gate. Okay, let's go ahead and try to write that. So we have that as VGS increases, electrons are attracted towards the region underneath the gate. And you can view that as electrons being attracted there, or the opposite can also be true, holes being repelled away, because when we are modeling electrons moving in one direction and filling holes, that means those electrons are leaving other holes behind, and so we can also view it as holes moving in the opposite direction. So either way you want to view it, it's electrically equivalent. Well, let's say electrons are attracted towards the region underneath the gate, filling available holes and creating, we refer to it as an inversion layer underneath the gate. The reason why we call it an inversion layer is because we have inverted the type of material. We initially had a p-type substrate, but by virtue of moving these electrons, we have created a region underneath the gate that looks like n-type material. It has excess electrons. Overall, the substrate is still neutral, but the layer right underneath the gate is now n-type. So the inversion layer, let me highlight that, that's important, underneath the gate. And this has created a resistive path between drain and source. Meaning it's just now a piece of n-type semiconductor, and if we apply a voltage difference, then current can flow, so we have a resistive path. We could model it as follows. We could say this is my oxide, that's my metal or poly, this is my gate. I'm applying my VGS voltage over here, and now what I have is essentially a resistive path between my drain and my source, so that current can flow if I apply a voltage. So in the current situation, nothing will happen because my drain and my source are both connected to ground. But let's say that now I apply a voltage at my drain terminal, VDS, and typically for a MOSFET transistor, all the signals are going to be all the voltages are going to be with reference to the source voltage. So in essence, what I have here is the following. My source is tied to ground, and this is tied to a voltage source VDS. And so as we expect, current is going to flow. Now, if you recall from your semiconductor theory, the resistive path of a semiconductor material, it's essentially a voltage-dependent resistor. Meaning the amount of current flow is going to depend on the amount of voltage that I apply at my VGS. So basically I have that if my VGS goes up, then my inversion layer becomes more heavily charged, if you will. So we have more of a positive charge or an M+ region, and so my resistance of that path will be lower. So my resistance will go down as my VGS increases. And then I have also the geometry of the channel. Typically for a wider channel, so the width of the channel goes up, my resistance will also go down. And if the length of my channel goes up, my resistance will go up. So the way we can represent my resistor is if I were to plot my output current ID versus VDS, voltage applied at the drain or voltage between drain and source, I will have that for a certain value of VGS, I will have no current. And so this will be one of the possible curves. And then as my VGS increases, I'm going to have some current with further increases in VDS, so some resistance. The resistance is going to be the inverse of that slope. And then as I keep increasing my VGS, my resistance is going to go down. And since this slope represents the inverse of the resistance, then that means the slope will be higher. So basically this will be for VGS1. This will be for VGS2 greater than VGS1. I've represented the case where I'm in cutoff, and I said if the voltage I apply at my gate is 0, then I will have no channel. But in all reality, it takes a certain amount of voltage to create that inversion layer. And that amount of voltage is referred to as the threshold voltage. Is the minimum voltage that I need to apply at the gate in order to create that channel or that inversion layer underneath. I'm going to make note of that. VT equals threshold voltage is the minimum voltage VGS needed to create an inversion layer, which we also refer to as channel. And so obviously that curve where the current is 0 will be for values of VGS that are lower than the threshold voltage. Now, once we have created a channel, further increases in VGS are going to give me lower resistance, so basically more current flow through my channel. And the amount of voltage that I apply at the gate, in addition to the threshold voltage, or the amount that I go beyond the threshold voltage, also receives a name, and it's termed the overdrive voltage. So the overdrive voltage, which we typically represent with VOV, is going to be the amount of voltage applied at the gate in excess of VT, typically represented as VGS minus VT. And so it makes sense to think that just as we have expressed how much our resistance in the channel changes by increases in VGS, we could also have said the resistance increases as we increase our overdrive voltage. So the case where the resistance is, or actually where the current is 0, we will have an overdrive voltage which is less than or equal to 0. And then this will correspond to overdrive voltage 1, and this will correspond to overdrive voltage 2 greater than overdrive voltage 1. So we can express things in terms of either just simply the raw VGS signal or the overdrive voltage, which is simply going to be the gate signal minus the threshold voltage. Something that is worth mentioning is that this type of operation applies to enhancement type MOSFETs. Enhancement types MOSFETs need have a positive threshold voltage when we're talking about an NMOS or N-channel MOS transistor. They have a positive threshold voltage that is non-zero, meaning you need to apply some positive voltage at the gate in order to create that inversion layer. There's another type of MOSFET called a depletion type MOSFET, and those typically have a channel already created before we apply any threshold voltage. So different fabrication, we're going to be dealing with enhancement type MOSFETs, and so we will be encountering positive values of threshold voltage required to turn on the transistor to create an inversion layer. Something perhaps important to note is that VT is going to be positive for NMOS transistors and negative for PMOS transistors. For PMOS transistors, you need to apply a negative voltage because what you're trying to do is not attract the electrons towards the region underneath the gate, but rather the opposite, repel the electrons from that region, so you end up with a net p-type region underneath the gate, underneath your gate. Typical values for the threshold voltage are going to be lower than 1 volt. Okay. Typically, VT is less than or equal to 1 volt. Now, so we have seen how we have created a channel by applying a voltage at the gate, and now I can apply a VDS signal between drain and source, and as I increase VDS, my current from drain to source goes increasing, and the rate of increase depends on the VGS value that I applied on my gate. It comes to a point, though, where as I keep increasing VDS, my channel starts tapering on the drain side. So in essence, what happens is as my VDS goes up, I'll represent it up here, my N-type channel starts taking a shape like this. I'm exaggerating it a little bit. A shape like that, where it's more tapered on the drain side. And the reason for that is as VDS goes increasing and gets close to VGS, the difference in voltage, or the effective voltage that's being applied on the drain side, is smaller. So there's less delta from the gate to the drain than there is from the gate to the source. So the gate voltage is higher with respect to the source, meaning it creates a wider, stronger inversion layer on that side than it creates on the drain side. As I keep increasing VDS, so it gets closer and closer to VGS, this phenomenon becomes more and more pronounced until at some point VDS becomes equal to the overdrive voltage, and at that point I get what's known as pinch off. And so basically what will happen is that the width or the extension of my inversion layer at the drain point will be equal to 0. So basically, we say the channel is pinching off right there. And so we can say this will be our number 1, number 2, that's what happens. Number 3, now that we have an inversion layer, as VDS increases, the channel gets tapered on the drain side, This causes the resistance of the channel to increase. And finally, when VDS is equal to the overdrive voltage, VGS minus VT, then we say the channel gets pinch off. And I'm going to highlight that term because it's a term of art. And at that point, it happens that as I continue to increase VDS beyond that point, I will observe that my current does not keep increasing with further increases in VDS. My current remains approximately constant. So it goes increasing, as we showed in the previous graph, with VDS until it reaches a certain point, which is exactly the point of pinch-off. And after that, if I continue to increase VDS, my current remains approximately constant. We say the transistor has entered saturation. So ID remains constant for further VDS increases. And you may think, well, that makes sense. If the channel is pinched off, then it will not continue to taper, and so it will just remain constant. The reality of it is that the channel actually, as you keep increasing VDS, the channel recedes, because if VDS goes higher than the overdrive voltage, then there is no inversion layer on that end. And then if you approximate that the voltage at each point along the channel goes decreasing progressively towards the voltage value of the source, then as you keep increasing VDS, more and more distance or more and more pathway from the drain to the source is going to be at a voltage that is greater than the overdrive voltage, and therefore there's going to be the inversion layer is going to start receding. Okay, that's exactly what happens. If you keep increasing past the point where VDS is equal to the overdrive voltage, now your inversion layer or your channel starts receding back. So you may wonder, well, why is it then that the current remains constant? Why doesn't it drop to zero after the pinch-off? Right? If we don't have a conductive channel any longer, then there should be no current flow. We have, in essence, a reverse bias junction. And the reason for that is as you increase the electric field from VDS, basically your electrons acquire sufficient kinetic energy that they are able to cross and make it into the drain region. And so the further increases are not due to the fact that there is, a conductive path any longer, but rather that these electrons are gaining enough kinetic energy to cross that, to bridge that gap. As you keep increasing the VDS, the channel keeps receding farther and farther, but the kinetic energy imparted to those electrons is higher. And therefore, both effects sort of counteract each other in a way that the net effect is that the current remains approximately constant with further increases in VDS. And so if I were to represent that graphically, what I will have is the following. This is my ID. This is my VDS. And again, we said there's going to be a certain value of VGS for which there is zero current, and that corresponds to VGS being less than the threshold voltage, the voltage required to turn on the or create the inversion layer or create a channel. And then for any other value of VGS greater than the threshold voltage, I'm going to, as I increase VDS, initially get a resistive type of response where there is a linear relationship between the voltage and the current. And then at some point, the current is just going to remain approximately constant for further increases in VDS. For higher values of VGS, this is going to have a greater slope, but eventually it will also reach saturation. So this will be for VGS equals VGS1, or I will just label it as VGS1. This will be VGS2, and this is the direction of increasing VGS, or again, we could express it as increasing the overdrive voltage as well. Obviously, there is a point at which the transistor leaves the linear or triode region, as this region is termed, where it behaves as a resistor and it enters that saturation region. And that point is going to be different because it's different for different values of VGS, because it simply is the point at which VDS equals the overdrive voltage. And so for a particular value of VGS, it will be here. For another value of VGS, it will be there. And so it forms, and I'll put it with a different color. It forms some sort of threshold or border, and that line represents the point at which VDS is exactly equal to VGS minus VT, or equal to the overdrive voltage. And that defines the border between the saturation region and the triode region. Triode region, sometimes often referred to as the linear region. I'm typically going to refer to it as the triode region so that we don't get confused with the BJT transistor, where we call the linear region what in the MOS transistor we call saturation. Obviously, the curve for which the inversion layer is not there, VGS is less than the threshold voltage, we call that the cutoff region, where the transistor is essentially off and there is no current flow. Now, for amplifiers, for analog amplification, the region that we're going to be operating our MOSFET transistor in is precisely that saturation region, where the output current remains approximately constant with respect to changes in VDS, and the amount of current is only dependent on the value of VGS. So basically the value of VGS, the gate voltage, or the overdrive voltage applied at the gate is going to determine the value of my output current. So I'm going to be interested in this region of operation. For linear amplification, we'll use transistors mostly in saturation region. And that's it. Next, we're going to take a look at a bit more quantitative description of the different regions of operation. Thank you.